Okay, so this is joint work with Damiano Brigo. He was meant to give the talk, but unfortunately couldn't make it, so I'm standing in for him. So hope I give a decent talk. So let's see how I move through slides. Okay, so the aim of the talk is, well, we can describe it in two ways. One is to give a coordinate-free definition of stochastic differential equations so that we can understand them more clearly on manifolds. Or actually, to be honest, my original aim in doing this work was I wanted to be able to draw a picture of an stochastic differential equation. And what I was looking for in my picture was that if I draw in some way a stochastic differential equation for some process x of t, and then I apply a function, some transformation, and draw the same stochastic differential equation for f of x, then this diagram should commute. So I've got the SDE, I've got my picture of it, and then the deformation of transforming my picture should give me the same result as Ito's lemma. So that was my aim. That was the aim of Damiano and I in this work. And you can see this is very parallel to questions what one might have in general in differential geometry, for a question like how do you draw a differential form? So we all know how to draw vector fields, that's easy, but differential forms are a little bit harder to understand. And the first aim of giving a coordinate-free definition, you can also understand that in terms of standard differential geometry. There are lots of different coordinate-free definitions of a vector field. There's also a coordinate definition of a vector field where you write out each component. There's something a bit more beautiful about understanding vector fields in a coordinate-free way. So that's the aim, to try and reproduce those things that people have done in differential geometry, stochastic differential equations. Okay, so we're not the first people to have done this. Stratonovich calculus gives you a way to define stochastic differential equations on manifolds using vector fields, but there is something a bit unsatisfactory about that probabilistically. There's also a technique called Schwartz morphisms, which defines stochastic differential equations in a way that's probabilistically better than Stratonovich calculus, but has the disadvantage of using quite obscure geometric ideas. And we're trying to get something between those two, something that uses familiar geometric notions but has better probabilistic properties. Okay, as I say, in the end we end up with something which has a few nice applications as well. So you can use the techniques I'm going to show you for practical methods of simulating SDEs. We've used it to define a notion of projecting SDEs. But I think perhaps the nicest thing and what we'll see today is visualization, simply. Okay, so this is this slide in itself really summarizes the main idea of the talk, which is that to define a stochastic differential equation, the first thing we do is define a field of curves at every point in the manifold. So here we've got, this is our manifold, we've got a curve at every single point. And that defines a process, once we're given Brownian motion W, and we start at a given point, and we follow the curve for a length of time given by the change in Brownian motion over a short time interval delta t. So we make a small movement, then we make another movement, another one, another one. And we're constantly following these curves, and the amount we follow the curves are given by these Brownian increments. So here's a formula for the curve that's followed. So essentially what we're doing is we're following the field of curves, but we're following it according to the steps given by Brownian motion. And that's the central idea. If we then take limits of this as time tends to 0, fairly unsurprisingly, this process converges. So we've got fairly large time steps here, and we're taking the limit. And you can see something that looks like a solution to a stochastic differential equation. So that's defined the process. We also now need to define what we mean by convergence. Again, we'd like a coordinate-free notion of convergence. So classically, one defines the notion of convergence using the metric on Euclidean space. So looking at the mean square distance between 2 points. And that's very much tied into the metric on Euclidean space, and that's not going to give us a very coordinate-free definition of stochastic differential equation. On the other hand, we could just take any Riemannian metric, and so long as our manifold is compact, all of those metrics are going to be equivalent. And so on compact manifolds, at least, we can come up with a coordinate-free notion of convergence. And the idea is to try and take that idea and generalize it to all manifolds by only being interested on the convergence on any particular compact subset. So choose a Riemannian metric on the manifold, and then we insist that for every compact subset we get convergence in mean squared within that subset, and then we just identify all the points outside of that compact subset to a point. And then that notion doesn't depend upon the Riemannian metric that you choose. So this is going to give us a coordinate-free notion of convergence. Okay, so we've defined a process in a way that's very coordinate-free. We've defined what we mean for it to converge. And one can prove that, that these processes converge pretty much all the time. So long as that field of curves is smooth, we will always get convergence. And so we've defined in a coordinate-free manner what we mean by a stochastic differential equation. So gamma here is our field of curves, and we've got this made up this notation of saying that x of t follows the curve. That's what that line, curved line, is meant to mean. So it follows the curves given by gamma at the line at the point x of t. So that's a coordinate-free definition of a stochastic differential equation, and I'll show in a moment how that relates to Ito stochastic differential equations. As an example, we could work on just the manifold R, and we could take as the curve at each point the curve given by s to the power alpha. So we're just going to move along a little power at each point. And in that case, you can solve explicitly the stochastic differential equation. So I'm trying to do that here. So we add in an increment of Brownian motion to the power alpha. Well, we know those increments are just some normally distributed random variable epsilon. We've got a sum of epsilon to the alpha, scaled appropriately by time. And so what's that sum equal to? Well, we know this from, you can see it from the central limit theorem if you like, that when alpha is 2, this is going to converge to just time. When alpha is 1, it's trivial. We just end up with Brownian motion again. And when alpha is greater than 3, it's just going to converge to 0. So what we see is that in the case of powers, the first two terms of any Taylor series are going to, if we look at the Taylor series for our curves, the first two terms are going to have some impact. So we're going to, the first term is going to give us something that looks a lot like Brownian motion locally. The second term is going to give us something that looks deterministic, and all higher order terms will vanish. So, writing this out, if we've got our curves gamma, we Taylor expand each gamma, and we expect the remainder term to be an irrelevance, and the motion of our process will be determined by the first derivative and the second derivative of our curves gamma. Well, the equivalence class of curves up to whether their first and second order terms are equal is what's called the two-jet of a curve. And it just generalizes the notion of a vector, which is the one-jet of a curve if they have the same first order Taylor expansion. So our definition, although we started with general curves, gamma, we actually only needed the two-jet of the curve. So we don't need to really define a curve at every point. We just need to define the two-jet of a curve at every point. And so that's the central coordinate-free notion of a stochastic differential equation, is to choose a two-jet at every point of your manifold, how you extend that to higher order is irrelevant to the convergence. Okay, so we've got this Taylor expansion that I showed you before. The first derivative, dWt, second derivative is associated with dWt squared. And our calculations using the central limit theorem suggest that in the limit, dWt squared will tend to delta t. I mean, this is something anybody who does stochastic differential equations tends to think of automatically. So we can write this discrete time scheme up at the top. We replace the dWt squared with delta t. And we now get a scheme that looks like the standard Euler scheme for a stochastic differential equation. And the limit of this scheme, so this is just a conventional Euler scheme, in the limit this will give us the standard Ito stochastic differential equation. So what we're seeing is that the first order term of our jet, so the first derivative, corresponds to this B term in a stochastic differential equation, a standard Ito stochastic differential equation. And the second order term here corresponds to the drift, this A term in the stochastic differential equation. So the diffusion is given by the first order term of your jet. The drift is given by the second order term of your jet. One thing I'd like to emphasize here is that this scheme, this discrete time scheme, hinges upon using the vector space structure of Rn. So we've got a plus here. We're multiplying by A and B. So this is the intuitive formulation of an Ito stochastic differential equation. This is the natural discrete time formulation of an Ito stochastic differential equation. And the vector space structure is just baked in there from the start. Whereas our original formulation of a discrete time scheme of moving along curves is just very coordinate free. So the essential difference we've made here is that we've started with a very coordinate free notion of what a discrete time scheme might be. The Ito approach starts with something that's very sort of rigid and staying in Rn. Okay, so this is the main outcome of this, is that we can now write down Ito's lemma in a very straightforward way. That if you look at a process X, and you've got some transformation of your manifold F, then what process does f of x satisfy? Well, the answer is you just apply f to each of these curves gamma, take composition of functions, and then the 2-jet of the composition of functions will define the stochastic differential equation satisfied by f of x. So this very neat expression, that if x follows the 2-jet gamma, f of x follows the 2-jet given by f composed with gamma, that's actually equivalent to the rather ugly but rather important Ito's lemma, which describes if your stochastic differential equation follows this process, then the process followed by f of x is given by this fairly grotesque formula. And so this coordinate-free approach is giving us a nice interpretation of Ito's lemma. And we can actually see that visually in this slide. So we've got a very specific curve gamma. This is the picture I showed you before, but I'm actually telling you the formula for each gamma here. So gamma is parameterized by time t, and it's a quadratic at each point, depending upon the point. So it's if we rewrite this in the more conventional Ito notation, then we're going to get this stochastic differential equation. So that's in terms of the field gamma, so we've specified what the curves gamma are. That's the equivalent Ito stochastic differential equation. We can then apply Ito's lemma to transform our variables. So we actually chose in this example, you can see it's got a nice radial symmetry. And it seems fairly obvious that if we make a transformation of this space to use polar coordinates, we're expecting to get a simplified equation. That seems natural. So if we make that transformation, if we use Ito's lemma to make that transformation, then this is the new stochastic differential equation that you get. And you can see it's rather simpler than it was before because these coefficients have each got a vanishing component. So we've divided it into just a pure drift term in one direction, pure Brownian motion in the other. So this is a nice simple equation. So that algebraically, we can transform using Ito's lemma and we get that result. Or, if we like, we can just deform the picture. So if we take this picture, apply the transformation given by changing to polar coordinates. I created this transformation just using graphical software. So it's just taken the image, it's just deformed the image completely blindly, knowing nothing about Ito's lemma. And then on the other hand, we've got the algebraic transformation of the SDE from one coordinate system to the other. And the nice thing is that this diagram commutes. So at each point here, we've got the little curves gamma, and you can see, okay, the shape of the grid where I've chosen to draw the curves has changed, but fundamentally, the curves gamma exactly match according to this transformation and according to the algebra. So we've got a nice picture that allows us to visualize Ito's lemma. And that I think was one of the main aims of this research, to try and understand that. So there's a slightly bigger picture of the same thing. Okay, well, you can now enjoy yourself having got this notion of an SDE as a two-jet. It's fun to start trying to rewrite all of these concepts like the forward and backward diffusion operator in terms of coordinate-free notions in terms of these curves gamma. And all I'll say now, because I'm running out of time, is if you do that, you end up with revealing formulas for these things. So this rather simple formula for the forward diffusion operator that's half the Laplacian is considerably simpler than the standard formula derived from just looking at the Ito formulation of the stochastic differential equation. Okay, so as a nice show-off picture that you can actually use this as a practical method if you have a practical reason for wanting to simulate Brownian motion on a pretzel. You can now do it by following these kinds of curves. And this shows how the idea generalizes. I've been looking at one-dimensional Brownian motion. This shows how you can generalize this to higher dimensional Brownian motions. So this clock face is a way of representing a map of R squared into a manifold. So we're looking at, instead of just being two jet of curves, we now have to look at two jets of maps from, say, R2 into the manifold. And this clock face allows us to picture that. And you can see this is Brownian motion because these clock faces appear to have diameter 1. If they were ellipses or something like that, it wouldn't be Brownian motion. So I think that picture's probably a good place for me to stop. Thank you.
Thank you very much for your nice talk. And are there any questions or comments?
How do you compute the curl field given the jet? Is there a general way to find one?
So given the two, so if you're given the two jet coordinates, then straight away that two jet will just be a quadratic expression. So if we look at this example, the curl that's been in front of you will be higher all the terms, it be a T cube term, something like that. But because someone's just giving me the jet, I'm only looking at the second order term, so I truncate it in my coordinate system, and that gives me, for a coordinate system, a canonical choice of curve. But obviously there's no, without the coordinate system, there wouldn't be a canonical choice of curve on the jet.
Thank you for the talk. I have two questions, but I guess probably they are both related. So I don't know if you could express kind of shortly how is this related to the work on the double tangent bundles of de la Cherie and Meyer. I don't know if you're familiar with that. And the second question, I'll just shoot it because it's related. You said this has some advantages over Stratonovich. Maybe you can. I can imagine it's related to that. So maybe you could phrase that if possible.
Yeah, so the question is, there are approaches that already exist. So Schwarz-Meyer is one, this double tangent bundle is another. They're all very closely related. And what people have done in the past is observe isomorphisms between geometric structures and the transformation rule of Ito's lemma. And this gives ways of understanding geometrically stochastic differential equations. So we're really just fitting into that same pattern and saying, instead of using something that's perhaps a little bit obscure, like the double tangent bundle or a Schwarz morphism, we're going to use this, we're going to talk about jets. So they're really just isomorphic geometric structures. And I think perhaps the big advantage of our approach, at least for me, is that we've got this discrete time scheme that allows us to interpret the results in a straightforward way. And it's actually that discrete time scheme allows you to start with but defining your process from the beginning in terms of these geometric structures, whereas that seems less clear with the other approaches. But ultimately, I think they're all equivalent in that these are all isomorphic geometric structures. They're all second-order structures and have very similar properties there. In terms of what's the issue with using Stratonovich calculus, I think it's that it just doesn't have a very nice probabilistic properties. For example, the Stratonovich integral is not a martingale. And so if you try and understand it in terms of this kind of discrete time scheme, it doesn't work very naturally. And I think perhaps whether you prefer Stratonovich or Ito calculus depends a bit upon your perspective. I come from financial mathematics, where we're very keen on the fact that the Ito integral is non-anticipative. That's incredibly important in finance. And so the Stratonovich calculus just doesn't really work very well in finance. And so I think there's perhaps a bit of a bias there. Whereas if I was a physicist and time is symmetric in both directions, which is not financially true, then maybe I'd prefer Stratonovich calculus. Thank you. Yeah.